Hey everyone, this is Miss Dunn. Hope you're all doing well during this unprecedented time, as people like to say. I miss all of you. I wish I were here in person, but of course that wouldn't be safe, so we'll have to do with this recording setup. As I go through, if you end up having questions about anything I say, don't hesitate to let me know either in some sort of comment, email, or Piazza. For now, I'd take a moment to pause this video and try the do now. Even if you feel like you know how to do it, maybe it's good practice. So go ahead and press pause, make sure you can do this kind of problem. Alright, so I noticed that this is a stoichiometry problem because I'm converting grams of one thing, grams of magnesium, and into grams of magnesium chloride, or rather the other way around. And I can see that my given, the way that we're used to doing it, is 190 grams. So 190 grams, and grams of what? Grams of MgCl2. And I need to turn that into grams of magnesium. You might remember, I know it's been a while, so it's alright if not, but grams, we don't like working in grams so much. So when we do stoic, we want to turn everything into moles. To do that, I'd use the molar mass. So I want grams on the bottom, so it cancels, and I'm going to turn it to moles. That's the molar mass. I don't know it off the top of my head. I'll look it up in a second. But this is moles of MgCl2. That's how many grams are in a mole of MgCl2. And there are 95.2. You get that from the periodic table in 1 mole. Great. Then I want to turn the magnesium chloride into just plain magnesium. So ideally I'd want to turn moles of MgCl2 into moles of Mg. How would I do that? I need to use the molar ratio. So remember that we get the molar ratio from the chemical equation. This tells us it's like a recipe, how many moles of one to the other, and there's no number in front of them, but that means there's just an invisible one there. So I need 1 mole of each. That cancels, and now I'm in moles of Mg. That's pretty close to my answer. I do want to end up with Mg. But what I actually want is grams of Mg, magnesium. So I'm going to use the molar mass one last time. Moles of Mg, grams of Mg, and again that's the molar mass. And the periodic table tells me there are 24.3 grams of magnesium in 1 mole of magnesium. Alright, so everything's all set up. I can put this into my calculator. So the 190 times 1 divided by 95.2, that's just 1 times 24.3, and I get something like 48.49 grams of Mg. Of course, we care about sig figs a little bit, so my given number over here, 190, only has 2 sig figs. The 0 at the end does not count because there's no decimal point. So I'd round that up, or down, sorry, to 48 grams of magnesium. That's how many I would need to perfectly react with the that's how many I would get if I perfectly reacted magnesium chloride with excess HCl, or as much HCl as I wanted. Alright, so take a moment there to think about how that problem went. I would say that to understand this lecture, because it's the last section in toxins, it's important to first make sure that you're comfortable with mole-to-mole conversions, 4.24, and stoichiometry with mass, not just mole-to-mole. That's 4.25 and the associated lessons. So I'm thinking that other chemistry classes didn't touch either of these topics yet, which is why you'll see a lot of links and resources to both of these topics in the Google Doc for week 1. So don't worry if that wasn't clear yet, or if you don't feel comfortable tackling that kind of problem. After you get to these 2 topics, I think it would that's when you would want to watch this video. Okay. So, 4.26, the last one, in toxins, limiting reactant and percent yield. Percent yield is actually something we talked about in alchemy, but it's kind of a reminder. And the title, Get the Lead Out, is just kind of like precipitating lead out of solutions. Okay, so the key question here being, what is a limiting reactant? Here come some notes. So, reactants are basically used up in a reaction, right? Or consumed. Based on the mole ratio, which is the coefficients in the chemical equation that tell you kind of how the recipe works. how much of each you need. So the one that is consumed first, used up first, the one that you run out of, is called the limiting reactant, because the limiting reactant determines how much product you can make. Think back to the sandwich analogy. There's that FET, I think it's linked in the Google Doc as well. If you have 5 pieces of bread and 1 piece of cheese, you're going to have some leftover bread. Your cheese is limiting. So that's what we mean by limiting reactant. So in this equation here, what kind of equation is it? A combustion reaction. Just remembering that because we make the carbon dioxide and the water. But the mole ratio between the reactants is 1 mole of the methane to 2 moles of the oxygen. And again, I can see that with the coefficients, there's a 2 here and an invisible 1 there. So if I have 10 moles of each one, which is limiting? And which one will be left over? Pause and think about that for a moment. Alright, so because you need more O2 than CH4, if I have the same number of moles of each one, I'm going to run out of my O2 first. So that's limiting, and then the methane, the CH4, is left over. So if that makes sense, if the concept of it makes sense now, now's the time to practice questions like this. I'm going to do an example of some problems, and then I think that your assignment for this week will be to do problems like this. Alright, so here is, you can pause and just do the problems yourself if you would like. I'm going to walk through them. Here we have an equation. It's the synthesis of ammonia using nitrogen gas and hydrogen gas. And the question every single time is which reactant is limiting. So if we have 6 moles of each reactant, 6 moles of each, it's kind of similar to what we did last time on the previous slide. If we have 6 moles of each, we have the same number of each one, and I can see that we're going to use the H2 up first because of its coefficient there. So because you need 3 of them, I'm going to use them up first, so H2 is limiting. Alright, if I have 6 grams of each though, that's not as clear to me. In fact, I wouldn't be able to do this off the top of my head because, remember, these coefficients are the molar ratio. So we need to turn these grams of things into moles of things. So let me do some math here. So 6 grams of nitrogen gas and 6 grams of hydrogen gas. These are going to be 2 different dimensional analyses on top and bottom of each other. So maybe I should make them different colors, sorry. Yeah, that'll work. Alright, so if I have 6 grams of hydrogen, I can turn that into grams to moles of hydrogen. In every mole of hydrogen gas, there are 2 grams of hydrogen gas, according to the periodic table. Let's cancel, and I have 3 moles of hydrogen. Alright, I have 3 moles of hydrogen. And then the nitrogen, it turns out I have, let's see, molar mass, 28 grams of N2 into 1 mole of N2. Well, I can see without even a calculator that it's going to be less than the 1 I would need to react with those 3 moles. But we get like 0.2 moles of nitrogen gas. And based on the molar ratio now, I need 1 to 3, right? I can see now that I don't have enough nitrogen to react with all the hydrogen. In this case, N2 is limiting. But there's no way I could do that off the top of my head because I would need the molar mass. I would need to use the periodic table and convert my grams to moles to figure out how the molar ratios work. Part C, there are actually a lot of ways to do it. You can again pause and try to figure it out yourself. I'm going to do a fairly longer way with dimensional analysis. I know that Dr. Anderson posted a video on the Google Doc that kind of does dimensional analysis with these kinds of problems. Mr. P also posted a video that does it a completely different way, which is totally fine, called rice tables. I'll talk about those in a second. But since we've been using dimensional analysis a lot, I'd suggest that you try it out and see how it goes. So I have 2 different, I guess one way to do it is like what we did in B. We could just figure out how many moles of each one we had and then use the molar ratio and figure it out that way. But oftentimes these problems will ask you to figure out Alright, now that you know which one's limiting, how much product are you actually going to make? Because again, stoichiometry is all about how do you turn your reactants into products. So I'm going to do something where I turn my nitrogen gas into the product, ammonia. Sorry, I'm going to turn my nitrogen gas into ammonia, like that. So let me just pretend it's a dimensional analysis problem with just nitrogen. How much ammonia could I make with 6 grams of nitrogen? Alright, so again, to use the molar ratio, I need to be in moles. So 1 mole of N2, and has 28 grams of N2. I just used that molar mass. And the molar ratio tells me I'll make 2 moles of NH3, moles of NH3 for every 1 mole of N2. And you're like, Miss Dunn, this is a lot of writing, and I agree. Again, if you want to take a slight shortcut on the writing part, you are welcome to, but if you find you're making mistakes very often, I would suggest that you write out what it's grams of, what it's moles of, to make sure that you're on the right track. So again, I use the molar ratio right here, and then I'm going to turn the moles of NH3 to grams of NH3 because I want to see how much product I'll make. Okay, so if I was just using 6 grams of nitrogen and I had a ton of H2, as much H2 as I wanted, I could make 7.2857 blah 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 sig figs. There's only one sig fig, so let's just say I'll make 7 grams of NH3. Not done yet. I need to figure out which one's limiting. So fine, I'll do that with the hydrogen now. Let's say I had 2 grams of hydrogen, and then I have to figure out how much ammonia I would make. So it's putting them under each other is kind of nice. Sorry, it's H now. Because I can just kind of copy the steps without even thinking about it too hard, as long as I change the molar mass. And then the molar ratio this time, I can see there's 3 hydrogen molecules, H2s, involved in every 1 NH3. And then, sorry, these are moles of things. Mole. And then, lastly, I use the molar mass again. And plugging that into my calculator, 11.3 something something, we'll just say even 10 grams of NH3. So again, you can pause and think about what that means. If I had 6 grams of nitrogen, I could make 7 ammonias. And if I had 2 grams of hydrogen, I could make 10 ammonias. So which one's limiting? Turns out that means that the nitrogen is still limiting. The nitrogen's limiting because I can't make as much of it. Think back to the bread and cheese analogy. If I had 5 pieces of bread, I could maybe make 4 sandwiches, or sorry, that's not correct, 2 sandwiches or something like that. But with 1 slice of cheese, I can only make 1 sandwich. So the cheese is limiting. It's preventing me, I don't have enough of it to make as much as 10 grams of NH3 in this case. So N2 is limiting here too. Alright, almost there. Again, this is basically the new content that you're responsible for this week. There's a different way to solve it with rice tables. It's very similar, I think, or it's similar in like idea, I guess. You should still understand the concept of it. Or rather, if you move to AP Chem, you will see things like rice tables, as well as dimensional analysis. Stoichiometry is a big theme in either case, but basically, you write out the reaction. That's what the R in rice stands for. You figure out how many moles of everything you start with. You do a change based on how much is used up, based on the molar ratio, and then do some subtraction, and then see what everything is at the end. And then you'll see which one's limiting based on which one runs out first. But again, Mr. P made a video on that, and it's linked on the Google Doc. Alright, one more sample problem / notes. Again, feel free to stop the video here if you feel like you get it and you want to try the formative assessment for this week. But percent yield, there's this formula where it's the actual thing divided by theoretical thing times 100%. What does that mean? Let's say that theoretically you were supposed to make 500 grams of carbon dioxide or something in a reaction, but in real life you only made like 250 grams, you can see that's not great percent yield, right? You only made 50% of it. So it's that times 100 equals 50%. So that's just what percent yield means. But again, feel free to pause, do the problem. I'm going to do the problem in a second. Alright, how do I get a new page on here? Great. Okay, here we go. So I need to figure out first what my reaction is. It's a combustion reaction. It tells me that in the problem, combustion reaction. And I guess I'll just write the reaction out first since I need to do it anyway. So combustion, C3H8 propane plus O2 makes, combustions always make the same thing, CO2 plus H2O. You just kind of got to know that. To balance it, because I would need to balance, so my C's, my H's, and my O's. I have 3 C's on this side, 8 H's, 2 O's, 1, 2, 2 in the carbon dioxide plus 1 in the water is 3 here. First thing I'm going to do, balance my C's out. So I'm going to put 3 of those. Don't forget to update your oxygen. So 3 times 2 is 6 oxygens in the carbon dioxide plus 1 over there. So 7. And then I'm going to update my waters as well. So I can see, or sorry, I'm going to update my H's because there's not enough on the right. So I'm going to put 4 over there. Now I have 8 of those, and then oxygens again, I have 6 from the carbon dioxide and 4, so 10 total. Looks like I just need 5 oxygens to get that. Great. So that's my balanced equation. This is what I'm going to want to use later on. Great. That tells me my molar ratios. It's a nice recipe. Back to the problem. The student used 100 grams of propane, 100 grams of propane, that's this reactant right here, and 100 grams of oxygen. Okay, that one right there. And in real life, the actual yield, the problem always has to tell you that. You can't, imagine it, unless you're doing a lab, in which case you would know what your actual yield is based on your measurement of your product. But in real life, you made 7.5 grams of the water vapor. What's the percent yield? How good of a job did the student do in the lab? Did they fully react their products, or did they let some of the water vapor evaporate off into the atmosphere, or disappear out of the beaker? All right. So I need to figure out which one's limiting in order to figure out the theoretical yield. Like, how much water would you have made if everything were perfect? If everything were perfect, there was some maximum amount of water you could have made in grams, because, your actual yield's also in grams. Okay, so I have 100 grams of each. Let's do 100 grams of propane. We'll do that one first. And I want to figure out how many grams of water. 100 grams of propane, how much water could it make? Oh, sorry, it's 100.0, I think. Matters just for sig figs, I guess, but 100.0. Okay, so grams to moles of propane. I'm not going to write all of them just because I'm getting a little bit tired of writing, but please let me know if you would like a version that has all of it. So that's 32 grams per mole, and that cancels. Moles of propane, that's not 32, I'm sorry, that's for the oxygen. 44.1. 44.1, and then I use the molar ratio to turn moles of C3H8 into moles of H2O. Again, the molar ratio can relate to any things in the reaction. So, according to my reaction, it tells me that there's 1 of those to every 4 of those. And then finally the molar mass of water, 18.01 grams in 1 mole of H2O. And doing all the math out, with this long thing, you can make, with this much propane, you can make 163 35, I think, but 0.4 because of sig figs. There's 4 sig figs here. So 163.4 grams of oxygen. Wow, it looks like we only made 7.5, so it doesn't look like you did a great job. Oh, but maybe the oxygen was limiting, right? Maybe oxygen was the problem. You weren't allowed to make that much anyway. So let's check the oxygen now. You do have to do both. And yes, these problems are long. So I have 100 grams of oxygen now. And now I get to use my 32 grams per mole Again, I'm being a little bit lazy on the molar mass, not including all the decimal places. And every mole of O2, there are my molar ratio is 5 moles of O2 for every 4 moles of H2O. And then, just like before, 18.01 grams of H2O per mole of H2O. Check everything cancels, should. Great. And then, with this much oxygen and infinite propane, I could have made 45.03 grams of H2O. Alright, so which one of these is limiting? They both have 4 sig figs, but which one is limiting? The propane or the oxygen? Right, should be that the oxygen is limiting because you can make you cannot actually make this much water. There wasn't enough oxygen for that. So you should have made 45.03. In real life, you made 7.5, so something went wrong there. Gotta practice some lab skills. Okay, and finally, it was asking for the percent yield, so I need to take the actual that you made divided by how much you should have made. So the actual was 7.5 grams divided by what you should have made, 5.03 grams. Somehow you lost some precision at the end there, but that's okay. Actually, no, you only had precision out to the 10th place no matter what. So, times 100, and that means you made 16.65 or 17 for sig figs percent yield. Percent yield was 17%. Not the greatest percent yield, but again, if you find an error in anything that I said, any of my math in particular, let me know. I do think that the setups are all right. If I mistyped anything into the calculator, just leave me a comment or, let me know on Piazza email, etc. Hopefully that's enough to help you solve the problems for this week. Again, this week is a little bit lighter for us because we've already covered all that prereq stuff. We covered this mole-to-mole and stoic with mass. Expect a little bit more in coming weeks, but stoic will come back. Stoic will come back even in weather, so it's something that's definitely worth practicing. I also have office hours, and all the other chemistry teachers have office hours. If you would like to set up an appointment on the Calendly link that I have in the Google Doc, or drop in on anyone else's Google Hangout hours, you can ask questions, we can do problems together. I think the tech will allow for that to happen. Or if you want to just, drop by office hours, and I think my office hours are 11 a.m. on Thursday, I believe. But we can also do something else if that doesn't work for you, just to chat. I'd be happy to. Alright, hopefully that wasn't too long. Have a great rest of your day. Continue to make sure you get outside in a safe way. Practice social distancing. Yeah. Thank you.